had an introduction to me. I've been with Ricardo now for 33 years. That turns into 1/3 of the company's existence. It's rather strange when one looks at it like that. My first lecture at the Institution of Mechanical Engineers was back in 1988. Things were very different then. Everything was wood panelled, including all of this podium and tables and so on. I feel like I should lean over here to be in line with the new furniture. We used to show 35mm slides. We had a pointer that was actually a bright light in a tube shining through a little slit at the end, and the tube got so hot you couldn't hold it. So things have moved on a little bit since that time. So what I'm going to do today is present our lecture, which is An Innovative Future, How 100 Years of Innovation Can Prepare Us for Tomorrow's Challenges. It's really in two parts. And those two parts really are looking back and looking forward. So looking back for the first half, I'll talk a little bit about Harry Ricardo and his characteristics. And to put some of the things that he did in perspective, I'll talk about propulsion technologies in the early 1900s. And that has certain parallels with where we are today, so I think you might find that interesting. Then I'll talk about the early days of Ricardo. To avoid listening to me all the time, we have a nice 5-minute video that takes you through some of the history and some of the innovations that Ricardo has done to explain a little bit more. And then after that, I'll move on to the future. So the current challenges and implications for propulsion technologies, where the issues are, and then what might the future look like. It's very difficult to look 100 years in advance, but I'm going to vary that between 50 and 100 depending on the topic. And I'm going to spend some time talking about our responsibilities as engineers. What do we need to do? How can we prepare for the future? How can we set ourselves up to respond the best way? And I'll finish up with conclusions. This lecture takes anything between 45 minutes and an hour, depending on how carried away I get on some topics, but I'll do my best to keep it reasonably concise. So, to start, Harry Ricardo, born in May 1885, He was one of the foremost engine designers and researchers of the internal combustion engine. But he didn't start off that way. His family business was actually in architecture, and he was training to be a civil engineer at Cambridge University when he got very interested in mechanical things and efficiency. And he actually entered a prize competition at Cambridge University to try and get the highest efficiency from a motorcycle. He won the competition despite having the largest engine, achieving 40 miles on a quart of fuel. Everybody remembers what a quart is, I hope. The equivalent of around 160 miles per gallon. And in his biography, he explains that that was one of the foremost things that happened to him in his career that really shaped what he would do in the future. To try and put this lecture in some context, I'm just going to start with what propulsion choices were available at the time that Harry Ricardo was at university. So these were generally the choices. You had steam, you had electric, and the early internal combustion engine. And just to quote something from Harry, which he wrote in 1902, there are 4 different types of engines for automobiles in general use: steam engines, electric motors, naphtha and other vapor motors, which are similar to steam engines in some ways, and hydrocarbon or internal combustion engines. Of these, steam is the most reliable because it is the best understood. So there we are, back in 1902. Steam is actually where the combustion engine was today. And we know what happened after that. If we were to compare those different propulsion systems, the electric vehicles were actually more popular. They were outselling gasoline counterparts by roughly 10 to 1 and accounted for approximately 1/3 of all vehicles on US roads at that time. They were clean, relatively easy to start. However, they were quite expensive. They had a limited range. There were limits on performance, and there were always issues with trying to recharge them. You could argue, well, what's happened so far? How much have we improved? The charging network in those days was relatively limited, and you had to live pretty near to a power station for it to be viable to charge an electric vehicle in those days. Steam-powered vehicles were reliable, as we described, relatively mature technology, but quite inconvenient. It took a little while to get your steam up. They were relatively dirty and not so good performance. The internal combustion engine, the primary benefit was its pretty good performance, very good range for a given amount of fuel, and refuelling was quite flexible. In the early days, you went and bought your fuel in a gallon can from a hardware store, but really development of the refuelling network was a key part of how the internal combustion engine won the race in the end. One of the big changes and the tipping point was probably the launch of the Ford Model T in 1908, and we've got a picture here. Some people have asked me about this picture. What is that young man at the front doing? Is he getting intimate with a Model T? In those days, you had to hand crank the engine to get it started, and of course quite inconvenient for many operators. There were lots of issues with early reliability. So this is the kind of context where Harry Ricardo was when he first started looking into the combustion engine. So a lot of promise from the combustion engine, but many challenges. So his main focus and his main hobby was researching the physics of internal combustion and the design of combustion chambers. And much of this led to some very significant developments, such as the use of octane ratings, the use of stratified charge. In fact, he applied a stratified charge system to an engine he designed and built in 1904, and learning about intake swirl, which we commonly use today. So these are very important things for him. He built a unique variable compression test engine called the E35 to develop this whole concept of what a fuel would do and when it would start to knock. And the work that he did to develop higher octane fuels directly led to Alcock and Brown flying the Atlantic in the Vickers Vimy bombers. Not many people know that, but that was a key link into this new octane. He explored stratified charge, as I described earlier, and also things like negative valve overlap. I mean, it was back in the early 1900s, very advanced for his time, and something that we regularly look at today. What I want to do now is show you some very early combustion photography that was done. It has some combustion in and shows how things have developed over time. The first frame show early attempts to characterize in-cylinder flow, and the unique way of looking at this was to put little wool tufts on the top of the piston and film it as the engine was turning over to see what was happening with the air motion. And it's actually narrated by one of our past employees, Murray Scott. Murray Scott was one of our most renowned diesel engineers who joined us in the 60s, and perhaps one of his claims to fame was he probably produced the very first diesel Jaguar. He was a very keen diesel engineer. He had a Jaguar, thought, why don't we put a diesel in a Jaguar, and did that all himself as his private motor car. That's how enthusiastic he was. So I'll just play this just to give you some idea of some of the early work.
This film of cotton streamers attached to the piston and head of a motored direct injection engine indicates slight inward motion before top-dead center and a reverse swish of much greater magnitude after TDC. It is interesting to note that the air velocities during the scavenge period have much greater influence on the cottons than does the squish.
So these are some later combustion results, very early combustion results with very high-speed photography. We dug out of the archives showing a direct injection system. Then we're going to show a more modern system, and then what we've been doing lately to actually model that and predict exactly what's going to happen. And we're comparing the two together here to give you some understanding of the correlation and what can be done. So the idea behind these videos is to show you how important that early work is and what was discovered during that time. Perhaps the best way to describe the origins of the Ricardo company is to look at this very first project that Harry Ricardo was involved in. We'll show a little bit more about this in the video, but the early tank engines in World War I had a lot of issues, very unreliable, and Harry was commissioned, because of his knowledge of early internal combustion engines, to completely redesign a new engine. It's a relatively large engine, a 6-inch bore engine with crosshead pistons. sure those of you who know engines know what the crosshead piston is. You have an extra link between the crank and the piston, so the connecting rod goes up and down vertically, and you can separate the lubrication from the piston from the lubrication to the crank system. And that proved to be a great success. That technique's still used in very large engines today. The ratings for the engine, anything from 150 to 260 horsepower, was by far the most powerful petrol engine available outside of aviation. Many hundreds were built, and we'll show a little bit more about that in the video. What was interesting was that the Mark V tank engine royalties enabled him to purchase some land to build our original Shoreham Technical Centre. This is a picture of the centre right in its very early formation stages. There's pretty much, I think, only one building still standing today, which is this one here. You might also be interested to know that this road along here was the main South Coast road at that time, with special passing places on the bridge, because it was single file. And that bridge is still there today, but no traffic goes over it, fortunately. So we can trace the beginning of the company back to a company that was formed called Engine Patents Limited on 10th of August 1915. This was around designing a new two-stroke engine, and with it the filing of Harry's first patents. It was a commercial approach he used throughout the business career with Ricardo and helped to fund his passion for developing new technology. As a result of all this work he did on the Mark V tank engine, the Defence Ministry paid Harry £30,000. Now, £30,000 in that date was worth about £1 million today in royalties. And that enabled him to purchase the land that now houses our Shoreham Technical Centre. He bought that for £225, about 10,000 today, and he spent another further 15,000, £500,000, building and fitting out his new research laboratory. So that gives you some kind of idea of the early stages of the company. To set up perhaps our video, which I'll show now, which describes how the company developed since its early beginnings and some of the innovations that were generated.
Ricardo, 100 years of innovation and technology. In 1915, the gentleman engineer Harry Ricardo founded the business which is today known around the world as Ricardo plc. From a very early age, Harry was interested in all things propulsion. He built steam engines as a child, and during his time at rugby school, his schoolmasters didn't know whether to commend or reprimand him when he fitted a steam engine to power his bicycle. By the age of 17, he had designed and built his first internal combustion engine to pump water from the well at the family home. He went on to study at Cambridge University, where he built his own motorcycle, joined the University Motor Club, and won their inaugural fuel efficiency trial in 1904, despite his motorcycle sporting the largest engine in the contest. Harry became one of the foremost engine experts of his generation and received a knighthood in 1948 for his work in the field of internal combustion engineering. He retired in 1964, but the company he founded continues his relentless drive for innovation and technology to this day. Our first major project was in 1915, when Harry was commissioned to apply his advanced combustion knowledge to the Mark V tank engine. Early tank engines created copious amounts of smoke, which gave away their position. Harry was asked to look at the problem. He decided that a new engine was needed, so he designed it himself. The new engine reduced smoke emissions significantly and was also much more powerful. In total, over 8,000 of these engines saw military service from 1917, making it the first British-designed engine to be mass-produced. Many combustion innovations followed. The turbulent cylinder head, devised during the winter of 1918 to 1919, was a low-cost combustion system that increased the power of side-valve gasoline engines. The variable compression ratio E35 research engine, developed in 1919, enabled the combustion properties of fuels to be accurately analysed and provided the groundwork for today's octane rating system. In 1931, the Ricardo Comet combustion system for high-speed diesel engines was developed, initially for AEC to use in London buses. However, such was its impact in reducing smoke emissions and improving fuel economy that variations of this system were still in use in the majority of diesel passenger car engines until the mid-1980s. The breadth of our expertise has grown and now covers all major vehicle systems, from engines, transmissions and hybrid and electric systems right through to complete vehicle design and production, such as the Ocelot Foxhound for the UK Ministry of Defence and the FED Alpha for the US Army. One of our most significant transmission innovations was the Viscous Coupling, which turned world rallying on its head in the 1980s in the pioneering Group B rally cars. The runaway success of these four-wheel drive cars established a whole new market sector for all-wheel drive passenger cars. We continue to supply engines and transmissions for many motorsport formulae today. We continue to deliver world firsts in four-wheel drive systems, and since 2001 we've assisted Bugatti with the design, development and manufacture of the highly advanced four-wheel drive dual-clutch driveline system for the Bugatti Veyron, the world's most powerful road car. Another world first was the record-breaking JCB Diesel Max. Powered by two JCB 444 backhoe-loaded diesel engines, we worked with JCB to boost the engines to produce a total of 1,500 horsepower in the JCB Diesel Max, which in 2006 took the FIA International diesel-powered land speed record at 350.092 miles per hour. In 2009, we collaborated with McLaren on the design and development of their 3.8-litre twin-turbo V8 engine. As part of the project, we also committed to creating a dedicated assembly facility to supply the engines within 18 months. The engine has twice been named International Engine of the Year in the 3 to 4 litre category. As well as engineering a wide range of transportation solutions, our business also boasts a rich history in delivering strategic, energy and environmental consulting services. For example, concepts from a 1953 report on deposition velocity are still used today as the basis of sophisticated computer modelling of the sources of atmospheric pollutants, their concentrations in the air and the exposure of populations and ecosystems to them. Our vision for the next 100 years is to deliver a sustainable future through our work in transport and security, energy and scarce resources and waste. We believe the world needs companies like ours, underpinned by a culture of innovation and a complete team of great scientists and engineers committed to making a real difference. Delivering excellence through innovation and technology. It's what we've been doing for 100 years.
Okay, works second time, which is good. So just as a summary, these are the innovations which were developed by Decade, some of the key things that we went through. As you'll notice, in 2006 we got the diesel land speed record for 350 miles an hour, but it wasn't the first land speed record. We also got a diesel land speed record back in 1936 with the Flying Spray. That achieved 159 miles an hour, so it was good to get it back again after a while. What I'm going to do now is move on to the second part of the lecture, which is all about the future. I'll start with the current challenges and implications for propulsion technologies and then look a bit further ahead. So to start with, what are the key challenges that we see going forward for our business? First one here is low carbon, affordable energy. Future energy is a major challenge globally, given the investment required to decarbonise the supply and make it affordable to the consumer at the same time. It's going to take vast investment to make that work, much more investment than we see required to decarbonise transport. Future mobility is also a very big core challenge when we must also decarbonise transport whilst improving safety and security. When we talk about safe and secure, we have to recognise that around 1.3 million people are still killed on the road every year, and 7 million are seriously injured. It's really something that we must do something about. In addition, we lose about 90 billion hours per year for drivers stuck in congestion and traffic. What a waste of time that is. How do we address that challenge? Increasing demand for consumer products also leads us to pressure on supply of scarce resources. We'll need to make much more efficient use of these resources using recycling and remanufacturing as a major strategy. And I'm going to go through these issues in turn. But I want to start really with mobility and the revolution that we're likely to see in connected mobility as well. So to start with, increasing requirements for developing these safe and secure vehicles will lead to a very rapid expansion in how we use intelligence and connected systems. This picture on the top left is one of my favourites. I use it quite frequently. Don't know if anybody knows where that is. I'll make it a little bit bigger for you so you can see it. It's not in the UK because they all drive on the right. This is actually Shanghai. And what is interesting about this picture is every exit of this roundabout is completely free and every entrance is absolutely jammed. Just goes to show that us as individual humans really need a bit of help to organise ourselves to make the best use of our road infrastructure. And that's what we're looking to do with the connected mobility systems. And I'm sure it's achievable. We also need to look at how we connect different forms of transport together. So whether we're running trains, rapid transit systems, vehicles, pedestrians, other forms of transit, making them seamless and connect together as well as possible is entirely within our capabilities in intelligent transport systems. We also, as I've described, need to massively reduce the number of accidents that occur. And to do that, we need to take away some of the human driver errors that we have, which are by far the largest cause of accidents. And that again will come down to how we use these intelligent systems, maybe to the point where the driver is not necessarily driving the car anymore. I'll say more about that later. Another big issue that we have is our resources and how efficiently we use our resources. Just as an example, I was over in the US last week, and the US model, don't want to be too critical of our US colleagues, we have many customers there, is a very linear model. You dig something out of the ground, you turn it into something useful, and then you throw it away. It's not really a very efficient use of resources. What we need to move towards is the circular model, the circular economy. So how do we recycle things? Using more of a biomimetic approach, how nature uses things. Having said that, we've made great progress in automotive. So automotive recycling is really a world leader. The 2015 End-of-Life Vehicle Directive sees material reuse at something like 85% just as recycled materials, and including the amount of material that is used again or recovered, including incineration, is around 95%. But the vehicle manufacturers are now responsible for disposal and reuse of the vehicle at the end of its life. And our view is that will extend to pretty much all products within a limited time. But it's a very important thing to grasp. We must also, when we're looking at future products, look at the whole product life cycle when we're assessing its impact on the environment. Just looking at its in-use emissions is too limited. We need to look at how much is involved in digging material out of the ground and processing it, how much in the manufacturing, how much in use, and how much in disposal. As an example, a modern electric vehicle has something between 1/3 and 1/2 of its embedded CO2 emissions actually in its manufacture. So to just look at its in-use emissions is too limited. And we need to change the way we look at these things to put in the right policies to drive the right behaviours. Another key area for us is vehicle energy efficiency. This shows CO2 emissions for passenger cars in terms of regulation and forward predictions of where those regulations will go in grams of CO2 per kilometre, normalised to the new European drive cycle. Many of you will have seen this chart before. There are some things you can draw from it. It shows many, many countries and their different regulations, but they're all headed towards a very similar position in terms of CO2 emissions. What you'll also notice is it's not the end of the regulation when we get to 2020 or 2025. Those regulations will continue to be more aggressive and drive even further improvements. And it's perhaps the rate of reduction that is the real challenge. In Europe, we have to achieve something like 3.9% per year improvement in CO2 to get us to the 2020 targets. In the US, it's 4.7%. And that is a real challenge, given their history of doing very little with CO2 emissions over the last 10 to 20 years. It's perhaps the biggest challenge. On top of this, we have to look at air quality. This is a history of air quality regulations both in Europe and in the US, and where we're getting to. You hear a lot about air quality in cities. It's still a major issue for us because of the increases in traffic that we see. However, we have made substantial improvements in air quality emissions from vehicles. We've reduced NOx from light-duty vehicles by about 98% compared with pre-regulated days. But we're still missing the air quality targets for NO2 in London. There's still a lot of work that has to be done. And as you might guess, we need to get these pretty much to virtual zero, to get to zero impact on the environment, which is the overall target. How long it will take us to get there, I'm not sure, but I suspect by the mid-20s we can say that modern vehicles have effectively zero impact on the environment from their combustion engines. And there'll be other things that we're probably more worried about, such as tyres and brakes. So what are the solutions? What things have we been looking at? We find these fall into two specific groups on how we're going to improve those CO2 emissions. The top four that I show here are largely about improving efficiency, and the bottom three about reducing the carbon content of the fuel or the energy that we use. So lightweight structures will be increasingly important. We drive around huge amounts of weight in our vehicles that are probably unnecessary, but we have to find an economic way to make vehicles lighter. The advanced internal combustion engine, probably connected in some way to electrification, will be the mainstay of our future power plants. All of the predictions I see show that by 2035 to 2040, something like 75 to 90% of vehicles will still employ some form of internal combustion engine. However, we do need to find a way to recover energy as we slow the vehicle down, rather than just turning into heat as we do with brakes at the moment. And we also need to find ways to use some of the wasted heat energy that we provide from the fuel. At best, the modern combustion engine only uses about 30 to 40% of the energy in the fuel. The rest is just thrown away, and we need to find ways of turning that heat into useful energy. There are alternatives to using conventional fossil fuels as well. We can run with electric vehicles, but we need to reduce the carbon intensity of the grid if we're going to make that effective. So we need to have low CO2 electricity. There's also an opportunity perhaps to produce renewable hydrogen from electricity, a relatively expensive process at the moment, and of course we don't have a refueling infrastructure. There's also an issue that many of the oil companies will argue that if there's any renewable hydrogen around, we should use these in the refineries. It's not well known, but about 2% of primary energy is used in refineries as hydrogen to purify our fuels and to improve the octane and fuel quality. And our friends in the refineries say if there's any renewable hydrogen around, please give it to us, because we can apply it to the whole transport fleet and you won't need to provide a new refueling infrastructure. So there are many challenges. Another alternative is advanced biofuels. How can we use either non-food based crops or perhaps waste products to develop or reduce the carbon content of conventional liquid or gaseous fuels? And that's going to be an increasing topic as part of the overall mix of how we reduce carbon. But still a major challenge because the amount of biomass is still very much limited. But the key message here is there is no silver bullet. We'll need a range of technologies. Despite the interests of many of our political leaders who think the solution might be we'll go out and buy an electric vehicle, that is simply not the case. There are many things that we have to work on to make this overall solution work. I showed you a picture earlier of the different vehicles that were available in the early 1900s. This is the position we're in now. We have a choice. There are a range of things that we can use. We have the internal combustion engine hybrid and plug-in hybrid, the fully electric vehicle, or the fuel cell vehicle. We have different boundary conditions now, but the interesting debate is which is ultimately going to be the winner. There are lots of challenges associated with electric vehicle, but for many applications they could be the solution, particularly in cities. A number of large automotive companies have decided perhaps the electric vehicle isn't going to make it. The challenges with batteries and energy storages are too great, and actually the best bet will be the fuel cell vehicle. And there are some significant trials underway in Europe and in the US to actually put some of those vehicles on the road in larger quantities to see how they work and how they interact. However, there's always the challenge that hydrogen fuel cell vehicles are always seen as the vehicle of the future, all the time. Every time it's the future rather than the present. So it'll be interesting to see how those might develop. And of course there's the internal combustion engine hybrid or plug-in hybrid. In some ways that's probably the best bet for the short to medium term. But we must remember that we've been working on the internal combustion engine for many, many years. Electric vehicle intensively only probably for the last 10 or 20, and the fuel cell's really been at quite a low level. And there's a lot more work to be done to turn this into a commercially viable product. In order to talk a little bit more about the future and where this all might be heading, we've tried to look at megatrends, looking at socio-economic and other megatrends and geopolitical trends to try and work out what the world will be like in the future. Ricardo is traditionally an engineering company, but since we bought an environmental consultancy, we now have a number of social scientists in our group who've really helped us with this. As you know, social scientists and engineers do struggle a little bit sometimes with communication, but we've done our best to try and get these into some concise and engineering-wise table. So first one here is population growth, 7 billion to 9 billion by 2050, and something like 60% of those will be Africa and Asia. That will have an impact, and the implication, even more demand for scarce resources, more demand for mobility and energy, and perhaps a change in geo-economic power. There's urbanisation. 2/3 of the world's population is predicted to reside in cities by 2030. And even more megacities. Even bigger challenge for urban people and goods mobility and what comes with that, which is overcrowding and congestion. So even more challenges. We're going to get increasing incomes and wealth. The prediction is that 60% of the world's population will be middle class by 2030 from about 27% today. What does that mean? A much improved access to education, better healthcare, and an increasing ageing population. It does also suggest more individual choice and freedoms and the rise of the individual. The big one perhaps though is connectivity, the exponential growth in volume and access to information, leading to all sorts of expected trends such as the interconnected global economy, growth of intelligent services and artificial intelligence. It's interesting, I've been looking, when I did this work, on where the next 50 years or so might go, at what the roadmap said 50 years ago for where we are today. And there was one thing that I drew from those roadmaps. All of them entirely missed the internet. They didn't discover it. They didn't know it was going to happen. So for any prediction in the future, my real challenge is what's the next internet? What's something that's bubbling away in the background that is going to significantly impact all of our lives? My best guess at the moment is going to be artificial intelligence. Being able to make much better decisions based on large quantities of data, multi-criteria issues to address, where the answers are very difficult to understand. I think that's really where this value is going to come in. There are some people who are quite worried about artificial intelligence. I know Stephen Hawking believes it's the biggest threat to mankind. My own view is it's a real opportunity to make a big step forward in how we address our challenges and make things far more efficient. One thing we should also recognise is that many of us who have teenage children live in a different world. They have different forms of social interaction. They're constantly connected to their personal devices. That's how they communicate. That's how they develop their friend networks. That's how they buy anything. That's how they sort out what services they might need in the future. It's a different attitude entirely to the generation that I came from, and it's something we must bear in mind when we look at the future. Another big issue, particularly for the younger generation, is the rise of the green agenda, climate change, air quality and scarce resources. The impact here is a significant growth of the circular economy and a complete intolerance of environmental damage. The polluter pays will become even more of an issue that will certainly grow punitive regulation to ensure that that happens. And this last mega trend is perhaps the more controversial, something I've discussed with our social scientists, this anti-consumerism. There is a view from some of the social commentators that our current passion with accumulating wealth and ownership of goods is something that might pass. You never know, could do. But mindless consumerism to improve work-life social balance, is that something that the next generation might decide is more important? So we need new attitudes to economic growth and a re-evaluation of wealth, and challenging the entire role of ownership. Do you ever own something, or do you just borrow it when you need it? It's that much more efficient way to do it. So bearing this in mind, what I'm going to do is try and go through what we see as the future mobility challenges, what we're going to do with energy, and how we're going to look after our resources. So to start with future transport, I've looked at 4 key driving areas. The first one being safety and security. So I've spoken earlier about road traffic injuries and fatalities, all those people that are killed. We have to do something about that. A lot of them are caused by human error. Increasingly, we'll see driver assistance systems moving on to automated vehicles that take the most risky part of that entire system out of the loop to automated vehicles. There are environmental challenges. We have to put zero impact on the environment. We need to reuse everything that we put into that vehicle. We need to look at how we remanufacture vehicles, not just completely deconstruct and rebuild them. And then how do we match the rate of technological evolution in information and communication technology to the mechanical systems that we have in mobility? How do we make those match? We have the infrastructure challenges, optimised road utilisation. We work in cities where, for some of the time, the roads are completely clogged, and then in the middle of the night, you can get around when you need to. How do we balance all of that and make it work? There's optimised space, use, and parking. How do you park your car? Where should you push it? Optimised vehicle utilisation. Most of us who own cars don't really use them very much. Of 23 and a half hours out of 24, that vehicle is parked by the side of the road doing absolutely nothing. That huge capital investment you made doing nothing at all. What a waste of resources. How do we address that challenge? And then, why do we always have to have the same vehicle doing everything that we need it to do, when really we need a different vehicle pretty much for many of the different things that we choose? On top of that, we have the next generation consumers, which I described, the connected generation. Many of these people in the connected generation have completely different attitudes to car ownership. My own children say they'd never really want to own a car. What's the point? If they're living in the city, why own a car? What's the purpose? And the vast majority of people are going to live in cities. They want increased options and choices, and very much into this connected world with on-demand services. If you put all of those things together, particularly the 4 at the end there, you end up with new value propositions, where vehicle manufacturers and vehicle providers end up as mobility service providers rather than manufacturers, and delivering instant availability. And the differentiator is how you connect with your customer and give them the service that they need. But we could end up easily by 2040 to 2050 with some key questions here. Why did we ever allow people to drive their own cars? How dangerous was that? Why did we let them do it? Of course, absolute mayhem. And then why would you ever think of owning your own car? What a limited prospect that would be. I think these are really 2 key points that we need to bear in mind for the future. Next kind of visualization here comes from the Shanghai Expo, courtesy of GM, where we're looking at on-demand availability. This is supposed to be 2030 vision. I think it's probably closer to 2050. Multi-connectivity here for the vehicles. Those lines in the sky are about communications. Utility on demand. You get any vehicle you want when you need it. Fully autonomous. You can do whatever you want in your leisure. will work. Platooning, pretty much a substitute for public transport. All the systems connect together. We don't need traffic lights anymore. Everything will avoid crashing into each other. Auto-charging, inductive, when vehicles need charging, they'll find a way of doing it. And then when you finish the vehicle, it'll either move on to go and pick somebody else up or go and park somewhere out of the way till it's next needed. So this is an overall vision of the future. 2030 might be a bit early. It's probably 2050, 2060, particularly with some of the infrastructure changes here, but I think it illustrates the point. But all of this has to be powered by some form of energy. What we've done here is put together a very simple cartoon of how the future mobility system might work. We're looking at three environments: the urban, inner city, and business districts, and how these are serviced by various transport means. We have our personal transport system in the urban area, which can communicate and drive into the city, or in the business districts as a platooning system. We'll have automatic parking and charging. We also have access at various points to commuter rapid transit systems, and where necessary, high-speed intercity transit as well. On top of this, we need goods mobility, and we see a separation between long-distance transport via urban hubs and inner-city deliveries and urban deliveries using different types of vehicles. But of course, we'll need different forms of energy to do these different forms of mobility. Increasingly, all of these systems will be massively connected via all sorts of communication systems and positioning systems with various forms of cloud processing to ensure we're using the infrastructure and the vehicles as efficiently as possible. So moving on to the energy, affordable low-carbon energy supply will require this long-term investment and various other drivers. So I have four key areas here. First one, availability. Really key thing for us is demand reduction and efficiency. We have a certain amount of that at the moment, but making buildings almost energy independent has got to be a major driver for the future. Living with zero waste. So if there is any waste, don't throw it away, use it for something, maybe waste the power, either turning it into liquid fuel or using it directly for heating. We have limited biomass availability, and we'll need to use it in the best place. Maybe that isn't in power generation, it might be in mobility. We also will have an increasing challenge of security of supply, the geopolitics involved. Many countries will be challenged with that particular issue. We'll have supply issues. Distributed renewables, increasingly important. Increasingly solar. Solar voltaics, solar thermal, using wind farms, local wind farms, bigger wind farms, all connected together, all of them controlled by the sun, of course. We'll need distributed and large-scale storage. Much of our renewable energy comes at the wrong time. How do you store that so you can reuse it, but we'll need to store it on a large scale and also on a small scale. Maybe there are new technologies. It may be within our lifetime that fusion becomes a commercial reality. Not sure that we should bet on that, but there's a lot of work going into that. Maybe there's some new physics that arise out of the latest physics experiments in the LHC. You know, they're the things that we can't predict for the future, but what we do know is 2050 we need to see an 80% reduction in greenhouse gas emissions. In terms of distribution, the supply network is a very expensive element in the system and something that's very difficult to invest in to see a return. So making our whole supply system bi-directional, connecting everything together, particularly some of the electric vehicles we have, maybe even converting some of this renewable energy directly to gas, which we can store either with hydrogen or synthetic methane by adding a carbon atom to it. And we really need to look at how we best optimize the use of the infrastructure we have from an energy perspective, not just the electricity grid, but the refueling network as well. Then we have the general economics, which is always the challenge. We need to continue to invest in low greenhouse gas generation. It's a very expensive thing to do. It's going to dwarf what we need to do on mobility. All the time we're competing with low-cost fossil fuels, which always end up to be the lowest cost form of energy. Dinging it out of the ground, always the cheapest way. We have to reduce the cost of renewables. A lot of work goes into that, a lot of work that Ricardo does as well, but all of it will require long-term, large-scale investment. And you get these, again, four things in the centre here, and the energy system in 2050 We'll see a range of supply and storage technologies, and almost certainly to move forward we need an integrated energy policy. The Chinese will be doing that, and all of us in the developed nations must get our handle on developing an integrated energy policy. However, the challenge for us in 2040 to 2050 is how do we do it? Is this all possible without large-scale regulation and market intervention? Probably not, on a much larger scale than we've seen in mobility. But is long-term investment and intervention beyond the capability of democratic government, who can only make short-term decisions? Somehow we need to find a way to follow the lead of the Chinese and have 20-plus year plans, particularly on infrastructure investment. Take it away from the short-term political issues that arise. Again, we've put together a cartoon of how all this fits together. So you'll see along the top a range of different supply systems, fusion heat and power, increasing wind, solar, wave and hydro storage, connecting that to distributed solar systems on the urban, city and business districts. We'll be incinerating any waste that we can't recycle to give us combined heat and power. Perhaps we'll have power to gas and heat and gas storage, either as methane or as hydrogen, and connecting that into industry and perhaps the urban hubs for transport. We will probably still need an element of fossil fuel, but much lower than we have today, and a very big industry in biotech and algal oils or similar to give us long distance, high density or high energy density fuels for our long distance transport. So all of this fits together into an integrated system, again using artificial intelligence to make all of the systems work as effectively together as possible. We look now at future resources and where those are going. We've talked about the issue over the linear and the circular economy. If we put a policy regulation, one of the key issues many governments are trying to address is resource security and resource nationalism. Probably many of you are aware that a number of magnetic materials are now restricted from export by China. They see that as a competitive advantage. And increasingly some of these rare materials will be seen as economic weapons. To address that, we need to look very carefully at resources and recycling, maybe some future regulations to drive the right behaviours, and an integrated resource and recycling plan together on a national basis to ensure that those products are used effectively. We've got business drivers. Every business will need to have a waste reduction strategy. How are you going to use your waste? How do you use it locally? How do you develop a sustainable supply chain with your local businesses? And how do you design right from the beginning for remanufacture, for reuse of your product rather than just scrapping it, splitting it all down and starting again? There are consumer impacts and drivers. Massive increase in demand for resources, not just material resources, but things like water. Our own prediction is by about 2050, 2060, we'll have passed this whole issue of CO2. We'll say, well, we solved that problem. The next challenge is we just don't have enough water in the right places to grow the food that we need and to give clean water to everybody so they're healthy. We need to look at resource sharing rather than resource owning and more positive attitudes to recycling. And then this massive change, perhaps led by the next generation, of a change in owning to leasing. Don't own things, borrow them, use them when you need them, and then give them back. And then there are economic challenges. The waste to liquid fuels is something that we need to do, but it's relatively expensive. We need to work out how to change waste to power and heat. How can we integrate that with business and domestic heating? And how do we allocate the right resource and waste responsibilities to drive the right behaviours? And you put all those things together, and the new paradigm is the linear to the circular economy and the zero waste environment. That's what we really need to drive. Next thing, 2040 to 2050, we'll ask the question, why did we throw things away and bury them? We're getting to the stage where in an average waste landfill, there's probably more value in the materials in that waste fill than in many, many conventional mines for rare materials. And we'll end up going and remining those waste dumps, try and get some of those materials back. We'll live with a situation where all resources and waste have intrinsic value which can be realised. So we never throw anything away. Again, a cartoon here to show how all this works. from domestic waste recycled through to materials, doing our landfill mining to recover the scarce resources that were previously thrown away, either recycling those materials or burning them, using them as energy or turning them into liquid fuels, supplying domestic, inner city and business environment, using Biotech, algal oils and some other renewable energies for biorefineries, again for recycling into zero waste or use in industry. And all of this leads to what we call the circular economy, just completely reusing the materials we've got. And increasingly, as we move forward, many of these issues are totally interconnected, whether it's mobility, energy or resources, all of them joined together. And you can show this with the last 3 slides, all put together. This is the connected system. This is the future where we're going to live. With all the different connections and complexities, understanding how to optimize the system is way beyond what we as humans can do. We'll need this level of artificial intelligence and optimization to actually work out what's the best way to connect the system and make it work as efficiently as possible. What I want to move on to now, getting towards the end of the lecture, is really about future engineering and our responsibilities. I've put 3 pictures up here. Hopefully some of you will recognise who these people are. This one, well known to us, Brunel, originally trained as a civil engineer. That was the key thing to be in the 19th century. This one is Henry Ford, mechanical engineer, the father of the motor car and future mobility, major entrepreneur. This one, Steve Jobs, again known as the latest generation of entrepreneurs, largely in the information and communication technologies field. Things are generally changing in that direction. So engineering was celebrated in the 1900s, but today our conventional view of civil and mechanical engineering has probably moved on. We always ask this question, what is an engineer? Is a mechanic? Is it a technician? It's one of the challenges we have with the future generation, is they think of an engineer as the guy who comes and fixes the washing machine, or helps mend some mechanical device, or mends the car when it breaks. We've increasingly got to show that future engineers are about very sophisticated technology, including all those communication technologies and sophisticated software that we talk about. The other issue we have is diluting our message. We have a plethora of professional engineering institutions, not just in the UK, around the world. I think in the UK we have 36 separate engineering institutions, all giving slightly different messages. How do we hope to convince the next generation that this is a very important, singularly well-organised profession when we're so diverse? How do we show that you're a professional? How do we compare the engineer to the lawyer or the doctor or the other respective professions? That's something that we really need to drive forward, but not from the issue of you design mechanical things. We also need to address this challenge that in the developing world, being an engineer is seen as a seriously good way to develop a career. It's the way to drive your way forward in life and to support your family. We need to change the attitudes here. For our centenary, we put together a book, a picture book, and as part of that, we interviewed a significant number of children in a class and asked them what was their view of the future, trying to get this view from the next generation, these 11 or 12-year-olds. Of all the children that we interviewed, which was a large number, only one of them wanted to be an engineer. Most of them wanted to be something in the services, some kind of either a musician or somebody who got famous. The celebrity culture thing is a real challenge for us at the moment. How do we show that there's a more rewarding career in doing something constructive? We need to show confidence in the future of the industry and address our skills shortage, and really engaging with the next generation to show them what we can do and how sophisticated our engineering profession has become. And we also need to address this whole issue of how do we get more girls into the profession. We're missing a whole part of the intellectual capital that we have. Unless we address that challenge, we'll really be struggling. And I get quite irritated sometimes by the view that the automotive industry in particular is an old industry that's going to die, and the new industries are going to be something to do with Apple or Google. and they're going to take over the world. I mean, we need to put some things in perspective. And I just put this slide in as an example of where we're going here. This is showing the million lines of code in various products that are commercially available. Down there on the left there, an F-22 Raptor fighter jet has about 1.7 million lines of code to make it work. 787 is 6.5 million. Just a premium car radio and sat-nav system takes around 20 million lines of code to make it work efficiently. A Mercedes-Benz S-Class today has 100 million lines of code. To put that in perspective, if you took 2 seconds to read each line and you didn't stop, it would take you 6.5 years to read the whole code in that system. The prediction is for a fully autonomous vehicle to make all of the mechanical and sensor systems and pattern recognition, everything work together, we'll need about 300 million lines of code for that kind of vehicle. On top of that, a premium vehicle will contain over 100 microprocessors networked throughout the car. That's more than an Airbus 380, apart from the audiovisual systems. The major future challenge we have is how we validate and certify a lot of the safety critical code in those products. How do we do it? Increasingly, we're unable to do the kind of physical testing that we used to do. I was talking to a chap from Bosch a couple of weeks ago. He said for them to certify and validate their next generation of driver assistance systems on the road takes 1 million kilometres of driving. That's simply not sustainable. What we'll need to do is develop the virtual world where this testing is done in a virtual environment. And that's a key requirement for the future generation of engineers, to move from their connected world and expand that into a virtual world that deliver us the future products that we need. So to finish up with some final conclusions here, we've shown a lot about innovation, but true innovation is born out of the need to meet enduring drivers, and those enduring drivers almost certainly the drive towards sustainability and zero environmental impact. And whilst legislation can initiate change, sustainable innovation always meets commercial requirements. Key statement here, in the real world, economics rules. If you can do it cheaper, you generally will. And we need to bear that in mind. Subsidies do not work in the mass market or in the long term. How do we make these things happen? Future solutions include a mix of integrated mobility, transport models, and energy resources. All of these things are entirely interconnected, and we'll need very sophisticated understanding and future systems to understand how to optimize those things. And we need a different attitude to the skills that we need for the future to meet these challenges, to meet these fresh innovations. Our future engineers need to adapt this massive increase in connectivity that they all understand to give us that future view of how we develop future products. So that concludes my lecture. Thank you very much.